to today's STERIS Tech Talk on industrial steam sterilization. STERIS Tech Talks are a series of webinars covering subjects relating to gas and radiation sterilization processing and the laboratory testing and validation services which support these processes. My name is Ashley Maroot, and I'm the Associate Product Manager for STERIS Applied Sterilization Technologies. I'll be the host for today's event. Our presenter today is Tim Skordahl, a Project Manager for reusable medical devices. Tim has served as a Project Manager at STERIS since May of 2015 in the Industrial Validations Group with a focus on steam sterilization and reusable devices, and is currently the subject matter expert for moist heat and dry heat sterilization, and also for processing of reusable medical devices. Tim provides technical and sales support for new projects, working closely with customers, account managers, and other groups across multiple business segments within the STERIS organization to answer any questions, provide cost and timeline estimates, and to ensure resources are available to support new projects. Tim is involved in AMI and ASTM standard organizations and has over 20 years of experience with process validations and medical device manufacturing and sterilization, having served in various roles at Biomed Laboratories, Laboratory Corporation of America, Biotest Laboratories, and the last 10 years here with STERIS. All attendees are on mute for the presentation. However, we would like to encourage everyone to submit questions using the questions function on the GoToWebinar control panel. Questions will be answered following the presentation. Today's presentation will be recorded and uploaded to our STERIS Applied Sterilization Technologies YouTube channel. Please note that continuing education credits are not provided as part of this webinar. And now over to Tim to begin the presentation.
Good morning, good afternoon, good evening, depending on where you are. I'm glad you're all here to join us for this webinar. I'm really excited to be given this opportunity to talk to you about steam sterilization. You can see here that I do have a bit of an agenda. We're going to talk a little bit about the history and background of steam sterilization. I'm going to talk a little bit about how steam sterilization works. We're going to talk about the pros and cons of steam sterilization, different types of processes that can be used with steam sterilization. I'll touch briefly on some validation options, and then I'll wrap up by presenting the main industry standards and guidance that are applicable to steam sterilization. So let's start with a history of the steam autoclave or steam processing. In 1679, French-born physicist Denis Papin invented a prototype of the autoclave, which was called a steam digester. This was basically a little more than a pressure cooker, but it did work to kill microorganisms. In 1879, French microbiologist Charles Chamberlain updated the steam digester to be used in medical applications and first coined the term autoclave. Then in 1894, J. Everett and George F. Hall started AMSCO International Incorporated and began producing steam sterilizers for healthcare. And in 1950, autoclave control systems were unified into an automatic push-button control, which made operation of the sterilizer much easier as opposed to turning valves and watching dials and having to actually manually operate the system. In 1979, AMSCO combined the steam sterilization process with a microcomputer, and the first computer-controlled sterilizers were developed and marketed. STERIS acquired AMSCO in 1976, so the AMSCO brand is now a part of the STERIS family. Now, steam sterilization is not a very widely used technology by comparison. As you can see by this pie chart, ethylene oxide comprises roughly 50% of the sterilization processing that's done worldwide. Radiation technologies, which include gamma, electron beam, and X-ray, they comprise about 45% of sterilization that's done globally. And then all of the other types of sterilization modalities, which include steam, vaporous hydrogen peroxide, ozone technologies, ultraviolet radiation technologies, and other novel technologies, they all comprise this little sliver of 5%. So you can see that steam is not a really big technology that's used, but there are some times when it is needed. And basically, I jokingly told one of my colleagues the other day that I was going to subtitle this presentation because sometimes EO and radiation just doesn't work. So that does actually happen where there are some products that you simply can't process in EO or through radiation. And oftentimes steam becomes the next alternative, the next viable alternative for sterilization of that type of device. So let's talk about some pros and cons of steam sterilization. There are advantages and disadvantages to this modality. One of the advantages are that steam sterilization is widely accepted globally. It's used in healthcare markets. It's used, somewhat, as we saw in that pie chart. It's used a little bit for industrial terminal sterilization, but it is widely accepted globally. The Center for Disease Control says that of all the methods available for sterilization, moist heat in the form of saturated steam under pressure is the most widely used and the most dependable. Steam, of course, is non-toxic. It's simply superheated water. Sterilization process is relatively fast when compared to some of the other technologies. There typically is no need for preconditioning or aeration to occur outside the chamber. You can sterilize slurries, gels, and liquids, which quite often cannot be processed in some of the other technologies. Steam sterilization has industry guidance and standards available, which comes in very handy. And the sterilization process is well understood. So of these advantages, I think one of the most important ones is the fact that you can sterilize liquids, gels, slurries, types of products using steam sterilization that you simply cannot sterilize in ethylene oxide, and you can rarely sterilize with radiation because quite often the radiation will cause problems with the actual liquid or gel or the slurry with cross-linking and polymerization and various other things. So it's important to realize that this is probably one of the key advantages to steam sterilization. Some of the disadvantages are that the sterilization process is not very well understood. So some of you might recognize that I've said both, it's well understood and not very well understood. To the layman, the process is pretty straightforward. I mean, we're talking about steam, we're talking about pressure, and it is fairly straightforward. But there are a lot of more technical aspects to it that aren't widely understood. We're going to touch a little bit about those later on during this presentation, so you can just start getting a feel for some of the more technical aspects of steam sterilization. Another one of the disadvantages are the high temperatures, of course. They range anywhere from 110 to 135 degrees C, which for those of you in the US is 230 to 455 degrees Fahrenheit. And then, of course, there's high pressures, which is 6 to 31 PSI gauge pressure, which translates to 21 to 46 PSI-A. One of the other disadvantages is that the chamber size is quite often smaller for steam sterilization than for most of the radiation technologies. Their carts are very big. EO technology has very large chambers. The largest chamber that STERIS operates for contract steam processing is approximately 1 pallet of volume. And this is roughly the same chamber size as the smallest EO chamber that STERIS currently uses. So we can go up to roughly 1 pallet. I know that EO processing chambers can get up in the 20s, I think maybe even 30 pallet chamber sizes, so they can get very large very quickly. With steam sterilization, it can be challenging to effectively sterilize devices with long lumens, such as long tube sets. Sometimes overly complex devices could present problems. Mated surfaces sometimes present problems. And then one of the key aspects to consider for a disadvantage is that materials cannot be processed in bulk shippers. So up here where I said the smallest EO chamber is roughly a pallet size, in that chamber they can literally drop a pallet into the chamber, and on that pallet will be 10, 20, or 30 cardboard shipper cases full of product. And you can just simply process it that way. You put it in the chamber, you pull it out of the chamber that way. With steam sterilization, you cannot process the cardboard shipper. And you also can't process, in most cases, a shelf box. So the individual devices in their primary sterile barrier need to be taken out of all of the packaging. And then in most cases, they're individually loaded into the chamber, which is very time consuming and labor intensive. And then they're processed that way, and then everything has to get repackaged before it's sent back to the customer. So that's definitely one of the disadvantages to consider. Some of the advantages and disadvantages for steam sterilization relate to material compatibility. So some of you might have seen this table. I think I've seen it many, many times in a lot of different presentations. It's widely used. I'm referencing this from MD and DI, which was published in March of 2006, where they talk about material compatibility between steam sterilization, radiation, and ethylene oxide sterilization. So you can see that there are a lot of good items that can be processed in ethylene oxide. Material compatibility is very widely accepted for ethylene oxide. There's a couple of no's and some varies over here for radiation. And then for steam, there's a pour and some varies and a pour and a no. So it kind of goes from right to left as far as the number of materials in this particular table that are compatible with that particular technology. So for those of you who are numbers people, what this essentially boils down to is that on this table there's 18 materials that are good for EO and only one that varies, and there are no pour and no cannot be sterilized with EO. For radiation, we have 13 of these materials that are good, 2 of them vary. There's 1 pour and there's 3 of them that you cannot process with radiation. And then for steam, you can see these just kind of keep on getting less and less compatibility. So we have 8 of these items that are good, 5 vary, 5 are pour, and 1 of them is a no. And for those of you in the room who are more visual and like charts and graphs, like me, this is just kind of a visual representation you can see up here for ethylene oxide. There's a lot of really good material compatibility. It drops down a little bit for radiation, and it's even less for steam. So now I want to talk briefly about how steam sterilization actually works inside the chamber. So this is a real high-level graphic representation of a steam sterilizer. What happens is that steam enters the jacket, enters the chamber jacket from the steam feed. The jacket is this space that surrounds the actual chamber. So steam will come into this space from the steam feed. And then the jacket pressure is controlled with a feedback loop. We have a pressure control and jacket pressure gauge. There's a feedback loop that monitors the jacket pressure and keeps it at the appropriate set point. And then steam from the jacket goes through this line and then enters the chamber behind the baffle. Once it goes into the chamber, it will often go to the top of the chamber, and the chamber will become stratified with steam at the top and air at the bottom. Because steam is lighter than air, it'll fill the chamber from the top and push the air down to the bottom of the chamber. As the initial stages of the process go on, air, steam, and water resulting from condensed steam are drained from the chamber down through the system drain. This representation is kind of an older model of sterilizer. Some of the newer models of sterilizers will actually have a separate steam feed for the jacket and the chamber. So in this instance, there's the steam feed that would come here and feed the jacket. This steam feed would bifurcate at some point and then would actually come into this line to fill the chamber, and they wouldn't actually be connected in any way. So most of the modern sterilizers are typically set up that way with separate steam feeds for the jacket and the chamber. So let's talk a little bit about how steam sterilization works. Basically, when you add energy to the system, you're going to turn water into steam. So this is what takes place in the steam generator or the boiler. You're adding energy into the system, you're turning water into steam. and that steam will contain a lot of energy. Now, under ideal conditions, whatever energy you put into a system, you'll get that same amount of energy out of the system. So you can see that as steam contacts, or steam is injected into the chamber, as the steam contacts whatever is inside the chamber, it condenses to water, which releases a huge amount of energy. And it's this energy that effectively destroys microorganisms by the irreversible coagulation and denaturization of enzymes and structural proteins. So there are different processes for different types of materials when it comes to steam sterilization. The two most common processes are going to be what's called a gravity displacement process, and the second is a dynamic air removal process. So with the gravity displacement, you have, at a high level, you have two variants. You have a fast exhaust and a slow exhaust. The fast exhaust is most often used for dry goods or hard goods, with few or no design challenges for steam penetration. Slow exhaust is often used for slurries, gels, and liquids in vented containers. And then for the dynamic air removal process, there's, at a high level, again, there's two different kinds. You have what's called a pre-vacuum, and then you have a steam flush pressure pulse, which is it's an SFPP, steam flush pressure pulse. The pre-vacuum is used for dry goods or textiles with design challenges that make it difficult to pull air out of the devices or the packaging or whatever is inside the chamber. The steam flush pressure pulse is also a dynamic air removal system, but this is primarily used for devices or packaging that can't withstand vacuum pressures. And then we have a couple of specialized processes. There's one that's called an air-cool cycle, which is very similar to a gravity displacement slow exhaust cycle. But during the air-cool cycle, the steam is removed from the chamber and is replaced with pressurized air. And then the jacket that we saw in the previous slide, steam is actually removed from the jacket and it's replaced with cold water. And this process is designed to cool the items that are in the chamber faster, for items that are somewhat heat liable and are not able to remain at high temperatures for long periods of time. And then another one of these specialized processes is air overpressure, sometimes called steam air mix. And this is used for liquids, gels, and slurries in non-vented containers, such as a crimp cap vial, or syringes, or a bottle with the cap tightly screwed on, flexible bags such as an IV bag, and then blister packs, something that might have like a foil lid on it or something where the steam can't actually get inside the blister pack. So the steam air overpressure works very well with these contained non-vented containers, in that it allows the materials to be processed without essentially exploding. Because when we are processing items in a steam sterilizer, there are some pretty dramatic pressure changes that take place at the front and at the end of the process. And these pressure changes, if not accounted for, will cause a non-vented container to rupture. So the air overpressure or the steam air mix processes are designed to mitigate that issue so that you can actually process these types of non-vented containers in a steam sterilizer. So with regard to actual steam sterilization processes, there are essentially three stages of a steam sterilization process. There's preconditioning, there's exposure, and then there's post-conditioning. So you can see by this chart that we have pressure over on the left side, time on the bottom, and temperature over on the right. So let's talk first about the preconditioning phase. The blue line represents chamber pressure, the red dotted line is chamber temperature, and the green dotted line is load temperature. So this preconditioning phase is essentially broken into two steps. The first step is kind of truly the conditioning phase. And you can see here we have some pressure pulses where the pressure is going down and then back up and then down and then back up. This is called a pre-vacuum or a pulse vacuum type of process. And you can see that in correlation with these pressure rises, we have peaks in chamber temperature as well as peaks in load temperature that occur with this pressure pulse inside the chamber. The second half of the preconditioning phase is called either a charge or heating up, depending on what type of sterilizer you're operating. And essentially what's happening here is that the temperature and pressure inside the chamber are brought up to the programmed exposure phase setting. So then let's move on to the exposure phase. And you can see that this is sometimes called a plateau period or a sterilize phase. The chamber pressure, chamber temperature, and low temperature are all in a plateau equilibrium state throughout the duration of the exposure phase. And then the third phase of the process is going to be post-conditioning, which is kind of broken up into essentially 3 steps. You can see here that the pressure drops down, and then once it gets below 15 psi, we're talking about vacuum pressures. And there's a dwell time down here, which is a vacuum dry time. And then this part right here is called an air brake, where we're bringing the chamber that is under vacuum back up to atmospheric conditions, and then the process has ended. So those are the 3 stages of a steam sterilization process. We have what's called a gravity process and a pre-vacuum process, which we've kind of already discussed. And we've also mentioned the SFPP, or the steam flush pressure pulse. We can see with the gravity cycle, basically we start the cycle and chamber temperature and pressure rise, it plateaus, and then the steam is exhausted from the chamber. It comes down here to atmospheric, where it draws a vacuum. It will enter a period of dry time, and the air brake back to atmospheric conditions. With the pre-vacuum cycle, again, we see we have these pulses where we're going up and down during the condition phase. In the sterilized phase, we charge, we plateau, and then we exhaust down to atmospheric, draw vacuum, do our dry time, and then air brake back up to atmospheric conditions. The steam flush pressure pulse, if you recall earlier, I said these are designed for items or packaging that cannot withstand vacuum. So you can see that all of our pulses are super atmospheric, whereas over here we have some subatmospheric and we have some super atmospheric. With the SFPP, everything takes place above atmospheric pressures. You can see we have some dwell time down here near atmospheric pressure, which is designed to just draw air out of the chamber and replace it with steam. And then we charge up to our sterilized phase, or our exposure phase. And then again, back down, we're exhausting, we draw vacuum, we dwell during our dry time, and then air brake back up to atmospheric conditions. So by looking at these slides, the pre-vacuum slide and the SFPP, we know that this previous slide that we looked at, we can call that a pre-vacuum because we can see these pulses down here. What's interesting, if you look at this, is that this is PSI-A, so atmospheric is going to be just slightly below 15 PSI-A. So you can see that all of these pulses are subatmospheric. So we're drawing a deep vacuum, we're going up to almost atmospheric conditions, we're drawing another vacuum, almost back up to atmospheric, and then we're drawing another vacuum. So everything takes place subatmospheric. Over here, we have superatmospheric, sub, super, and sub. And then over here, everything is super atmospheric. So there are different types of dynamic air removal processes, and they're all used for different functions. And actually, some of the newer healthcare models have kind of a hybrid where the first half of the conditioning phase is all done with subatmospheric pulses, and the second half of the conditioning phase is a series of superatmospheric pulses. So there's many different ways of doing this that all effectively work to pull air out of the chamber and replace it with steam. So the whole purpose of the precondition phase is to get all that non-condensable gas, all of that air out of the chamber, because that's the greatest enemy to steam sterilization, is going to be residual air. So the whole purpose of these pressure pulses and vacuum pulses is to pull air out of the chamber, flush it down the drain, and replace everything with saturated steam. So let's talk a little bit about the lethality of steam sterilization. A few weeks ago, a colleague of mine, Richard Kalman, presented a webinar on the fundamentals of ethylene oxide, and he shared this slide where we can see that the factors that affect the lethality of EO sterilization are temperature, humidity, gas concentration, and exposure time. So let's look at the factors that affect the lethality of steam. First, we have temperature, then we have humidity, and there's also gas concentration. And can you guess what the last component is? If you could talk, you would probably be saying, yes, it's going to be exposure time. Yes, you're absolutely right. Now, since we're talking about steam sterilization, humidity and gas concentration can essentially be combined into what's called pressure. So the factors that do affect the lethality of steam sterilization are going to be temperature, pressure, and exposure time. So what is the effect of temperature on steam sterilization? Well, when we're talking about a saturated steam environment, we can't discuss temperature exclusively when dealing with a saturated steam environment. Steam temperature and pressure are inextricably linked. So they have what's called a saturated steam table, which is what I'm showing here. On the left, we have pressure. On the bottom, we have temperature. We can see that as temperature increases, pressure also increases. And this is a well-known engineering process that's well understood. When you have temperatures at roughly 110 degrees C, if it's a saturated steam environment, your pressure is going to be roughly 6 psi-G. Similarly, at 121 degrees Celsius, you're going to have roughly 15 psi-G. So as pressure increases, so does temperature. Likewise, as temperature decreases, pressure must also decrease. So this is temperature and pressure. What happens when we talk about temperature and time? So when we talk about temperature and time combined, this is essentially what's called accumulated lethality. The shorthand for accumulated lethality is F sub 0. So some of you might have heard that term thrown around and wondered, what is F sub 0? Well, it's accumulated lethality. And typically, F sub 0 keys in on a universal reference point of 121 degrees C, which is just kind of, at some point someone decided that 121.1 C, which is 250 degrees Fahrenheit, is going to be the primary reference point for steam sterilization. So F sub 0 basically means that at 1 minute of 121 degrees Celsius, you will have accumulated 1 minute of accumulated lethality. At 2 minutes, you got 2 minutes, and so on down to 30 minutes. A 30-minute process is a fairly standard cycle at 121 degrees where you've got 30 minutes of accumulated lethality. Now, what happens when we increase the temperature of a sterilization process? At 132 degrees C, we can see that we acquire F sub 0 or accumulated lethality much faster. So over here at 121 degrees C, it took 30 minutes to achieve 30 minutes of accumulated lethality at 121 degrees C. At 132 degrees C, we can see that somewhere between 2 and 3 minutes, we have acquired 30 minutes of F sub 0. So what that means is that at roughly 2.5 minutes of time exposure at 132 degrees C, we have effectively delivered the same amount of energy, the same amount of lethality, the same amount of sterilization to a process at 121 degrees C for 30 minutes. So those two processes would be considered essentially equivalent as far as their lethality goes. So I chose 4 minutes because that's a very common time at 132 degrees C, probably more so for the healthcare industry. When it comes to industrial steam sterilization, of course, we're free to use whatever time we need necessary to sterilize a product. So what happens when you decrease the temperature? So steam sterilization can actually be operated down to temperatures around 110, maybe 105 if you've got a good steam sterilizer. But just like over here, when you increase steam and you reduced time, if you decrease the temperature, you have to increase time. So for those of you that don't have an eagle eye, this is actually 387 minutes of exposure down here, which is roughly 6.5 hours long. So what that means is that at 110 degrees C, you would need to process your load for roughly 6.5 hours in order to achieve the same amount of sterilization activity than you would have achieved at 30 minutes at 121 degrees C. So that's how accumulated lethality works. There's a lot more to it than that, but this is kind of a high level, I just want you to understand what people are kind of talking about when they talk about accumulated lethality or F sub 0. Now I want to touch briefly on validation of steam sterilization processes. There is the traditional validation process, which looks very similar to what you would see for an ethylene oxide sterilization process, where you've got a half cycle overkill. You're running 3 consecutive microbiological performance qualification runs, or MPQ runs. These are typically half cycles. There will be BIs in these cycles that will have usually in excess of 1 million organisms for your indicator organism. And then you're running half cycles with the goal of killing all of those BIs in a half cycle, so that you know that if you do a full cycle, you will have a process that's twice as efficacious as that. And then after you get done with your MPQ runs, you'll run a series of physical performance qualification runs. And these runs are typically used to generate process data for routine process tolerances, so that when you're validating a process, you know that when you're doing actual production processing, you'll know from your validation results that you have to have this amount of exposure time at this certain temperature and no more than that or no less than that. We started also talking about temperature and pressure rates of change and different aspects that impact lethality that we didn't kind of get into previously. So the PPQ runs are done to generate those tolerances. Now, this triplicate MPQ and triplicate PPQ runs is operating under the assumption that you have a fixed load configuration. Oftentimes, we'll have products or customers that want a variable load configuration, so they want us to be able to either send 20 units or 200 units to be sterilized. They want that flexibility in their lot size. So when that happens, we actually want to execute 3 MPQ runs with the minimum load configuration, followed by 3 MPQ runs at the maximum load configuration, so that we're bracketing that variability and understanding that it works, that this process is effective with the minimum load as well as the maximum load. And then by extrapolation, we can say that anything in between those will also be effectively sterilized. We would also do the same with the PPQ runs. We want to know if a minimum load configuration has different physical characteristics than the maximum load configuration. So when we get down to routine processing, we don't want to do all of our PPQ runs at either the min or the max, and then find out that when we start seeing some load variability, some of our tolerances are no longer applicable because things have changed. So we want to bracket the minimum and maximum load configurations when we're talking about a variable load. And then one of the things with steam sterilization is that you can validate a process using parametric release, which essentially means that you don't have to wait for biological indicator testing for each production run. You can strictly go by the time and temperature and pressure data that you generate from the sterilizer strip chart to show that this process ran the same way as the processes that were done during the process validation, so we can be assured that the materials inside that run have been effectively sterilized. Now, there are a couple of alternative approaches to process validation that are identified in ISO 17665-1. So there's the bioburden-based method, which demonstrates process efficacy against a fully characterized biome or bioburden of the materials being processed. So there are actually no biological indicators that are used during this validation approach. You're actually basing the efficacy of the process on the known and fully characterized bioburden that are on the devices prior to sterilization. So one of the drawbacks of this method is that it requires intensive bioburden testing of each production lot. You have to make sure that what you're putting into the chamber does not present a greater bioload or a greater challenge to sterilization than what was validated using this bioburden-based method. There's also the combined bioburden biological indicator method. This process demonstrates efficacy against both the bioburden and a reference organism. This reference organism might not necessarily be Geobacillus stereothermophilus. I know that word is a mouthful. It's the first time I've used that term. Geobacillus stereothermophilus is the primary indicator organism that's used for steam sterilization. It's determined to be the greatest, it presents the greatest resistance to steam sterilization. But when you're using the combined bioburden BI method, you might not necessarily use Geobacillus stereothermophilus. You could use, for instance, Bacillus subtilis with a known D value that is much less, excuse me, is much less than Geobacillus stereothermophilus. And quite often when I'm dealing with products that the customer or the product themselves need to be processed at lower temperatures below 121 degrees C. So the previous slide, when we looked at 110 degrees C and we saw that 6.5 hour cycle, if we use a BI that is less resistant than Geobacillus stereothermophilus, we can actually bring that cycle back down to a manageable 30 to 60 minute process and still demonstrate an effective 6 log organism reduction during a half cycle, resulting in an SAL of 10 to the minus 6 or better, using that organism that's a little bit lower resistance. And then finally, there's the full cycle approach to the overkill method, which is in the same annex as the half cycle. And this uses a BI with higher resistance characteristics than the minimum required for the half cycle overkill approach. So there's a series of industry standards out there that deal with how to manufacture biological indicators and what the minimum requirements are. And those standards state that for steam sterilization, you have to have a minimum of, I believe it's 1 times 10 to the 6th organisms, which is essentially 1 million organisms or more on each BI. And then the D value or the resistance of that organism must be greater than or equal to 1.5 minutes, which means that it takes 1.5 minutes at 121 degrees Celsius to reduce the population from 10 to the 6th down to 10 to the 5th. I know that's a lot of information. I'm not going to get into a lot of detail on that right now because that's not the purpose of this presentation. But for the full cycle approach, if you have a BI that is substantially more resistant than 1.5 minutes, if we're talking about something that's in the range of 2 minutes, 2.5 minutes, or even 3 minutes that it would take to reduce that population by 1 log, then you can use that biological indicator and actually execute full cycles and not do these half cycles that a traditional approach would require. Finally, I want to wrap up this presentation with talking about some of the applicable standards and guidance that are available. So we have ISO 17665-1, which was originally published in 2006 and reissued again or reaffirmed in 2013. And this is titled Sterilization of Healthcare Products, Moist Heat. A very good guidance on technical aspects of steam sterilization and how to validate and control processes. Then there's ISO TIR 17665-2. So TIR stands for Technical Information Report. This means that this guidance essentially tells you how to use and apply 17665-1. So it's a really good guidance to reference if you have any questions on what's going on in the -1 document. 17665-3 is also a technical information report. This isn't very widely used to the best of my knowledge. If you're a larger company that has many different types of products that you are sterilizing in steam sterilization, you might want to consider pooling them into a product family. This guidance tells you how to do that so that you can use one type of process to sterilize more than one device in a product family. So going back to earlier in this presentation where we saw that steam sterilization comprises, maybe 1 or 2% of the total market for sterilization technologies, you can imagine that TIR 17665-3 probably is not really used all that often. And in fact, I use this standard almost exclusively for the reusable device industry and not so much for industrial steam sterilization. And then over in the second column here, we have AAMI TIR 17, which is the compatibility of materials. The earlier slide from the ND&DI article back from 2006 talked a little bit about material compatibility. This technical information report is very good. It doesn't only deal with steam, it also touches on vaporous hydrogen peroxide and EO and various forms of radiation. It's a good report, good information presented there. And then finally, we have PDA technical report number 1, which is actually a really, really good guidance document. I like this one a lot. It provides a lot of really good definitions. It provides a lot of really good background. It goes into cycle development, cycle design, how to validate processes. And I really like this guidance a lot. So if you don't have that one and you're interested in steam sterilization, it would be a good standard to get a hold of.
Thanks again for joining us today, and this concludes the webinar.